Good morning, everyone. So today we look at another problem that is also simple in beam theory, and again we will use symbolic elements there. So this one has concentrated moment and just one of them. So you can see how simple we use the same principles that we look in the previous video. Um, Here we have a simple supported beam. We do have a roller on the right side and a pin on the left side, and right in the middle, a concentrated moment M naught. So again, the first um, step we do use it to find the support reaction. Then the second one will be to build the shear diagram, and the third to build the moment diagram based on the shear diagram. So when we look here, it's easy. Again, we isolate the beam and we put the support reactions there, and using again Newton's second law, again we observe that there is no horizontal load there, so that basically it simplifies a little bit the problem. And then when we solve for sum of forces on y direction, we figure it out that ay is negative in this case. So that's what I consider here positive. So then I flipped it going downward just to simplify my work on the shear diagram. So I'm going to use this free body diagram on the next slide, and that will help me out to build the shear diagram. So again, wherever we have a concentrated force, we will jump upward or downward as the force is telling us. And as we move along a segment, we will use this derivative equation, differential equation. So very simple to look at. Point A, the AY shows us that we need to jump downward with that amount m naught divided by 2L, which we do it right here. And then we look at that differential equation, very simple first order. And it tells us, because we don't have any distributed load here along the beam, that means we should have the slope of V, it's going to be a 0, which means it's a horizontal line, which we do have here, no change in the shear diagram all the way to the end, where we meet cy that tells us we need to jump upward the direction of cy with the same amount, and we end up in 0. We start from 0, we end up in 0. So the shear diagram, it's we can see that it's a negative shear all the way along the beam, and it's constant. Now we move on the next step, building the moment diagram based on the shear diagram, which we developed in the previous slide. So, and now we focus on the concentrating moments in this case. So at point A, there is no moment whatsoever. So basically, we start from 0. And as we move from left to right in segment AB, then we use again the differential equation we have here and utilize the shear diagram we just built. So basically for that segment, we see that the sign of the shear diagram is negative, and the magnitude of the shear, pardon me, it's constant. So we are supposed to have a slope that is negative and constant for the moment, bending moment. That means being a constant, the slope, it means that the line, it is a line with a negative slope. So that's exactly what we can see here. That's a line, and that has a negative slope, not a positive. It doesn't go that in the in the first quadrant. It goes in the fourth quadrant. In other words, right here that you can see, fourth and second quadrant, it's a negative slope. And then the question is, where are we going to land at this moment right here? And again, for that one, you recall we have that change. We have this equation, so we have when moment in B is going to be equal with moment in A plus the change from A to B, with meaning that we have to integrate that equation, and that is basically supposed to calculate the area under the curve of the shear force, which is right here. And you can see when we are doing it that way, because it's a negative, that's my rectangle right there. I will calculate the area of that rectangle. Very simple, and I have to account for the negative sign here. It's a negative load after all there, and then very simple to calculate. And again, we find the moment at point B in this way with this equation. Then this moment right here, it's a concentrating moment, which is clockwise this time. It means that we are jumping upward when it's clockwise based on our convention with the same amount of the force of the moment m naught. So we can see that we jump from this minus m naught divided by 2 with m naught to plus m naught divided by 2. And again, the segment moving forward from here, we look at the same equation, same situation, negative, uh, a line with a negative slope. And again, you guys can see the line here has to have this slope, which is basically the value everywhere. It's going to be the value of the shear force, which is constant for us. It's this is the slope. I didn't put it there. And we are supposed to calculate where are we landing at the end of so we are supposed to not have any moment there, but when we do so, we see that in moment in C it's going to be equal with the moment in B right there. And I kind of put here, as you guys can see, moment at the left of point B at moment of the right at point B, because right there at point B we have that sudden jump right there. So we'll start from here after the jump, and that's the right point B. So again, the change in the moment will be the area under the shear curve. This will be this. I'm saying under, but is we do see it's above in this case because the curve is underneath the axis anyway. So we can see that this is the area of this green rectangle. Easy to calculate again, and then we are getting the diagram. I hope this simple video shows you how clear, in a clear mode, clear way that we can solve these problems, very simply with these principles from the beam theory by using the jumping, or when we have concentrated loads, and these equations, differential equations, both for shear and for the moment diagram. Have a beautiful day.